morning. Today I am going to start the topic probability theory. Now, the terms such as chance, randomness, uncertainty probably have been in use since time immemorial. People realized long back that things do not happen as planned. So, I am giving some examples of uncertainty in events, like what will be the weather tomorrow. So, whether it will be rainy day, whether it will be very cold, or whether it will be moderately cold, or whether it will be warm, or whether it will be cloudy. So, this is uncertainty. A child born today, what will be the height that he will achieve when he or she is adult? So, we know that in everyday life we cannot predict that what would be the actual height that an adult will achieve. So, this is uncertainty. We can consider, for example, what would be the total amount of food grains production this year. We may have a fixed area or fixed amount of seeds sown for a particular crop, but the ultimate food grain is dependent upon various things. For example, what is the irrigation, how much is the fertility, whether there are any natural calamities during the year, etc. So, the total amount will be variable. We can never predict the complete age of a person. So, a person may be very healthy, but still he may die young due to various reasons. A person may be a precarious, but he may actually live much longer. During a cyclone, what is the height of a storm surge? If we take a medicine, suppose you get a common cold and you take medicine, but how much time you will take to get cured is not certain. What would be the blood pressure of a person? So, we measure the blood pressure when a patient goes to a doctor. So, what is the actual, whether it is 120 by 80, whether it is 130 by 90, whether it is 115 by 75, etc. So, that is uncertain. What is the when we conduct a exam, so how many students score how many marks? So, this is uncertain. So, for example, I have written how many students score more than 75% marks in a test. Similarly, whenever we consider any mechanical, electrical or electronic equipment, then what is the total life of that? So, for example, if we are considering a tube light, what is the total life, say in hours, whether it will light for 100 hours, whether it will light for 500 hours, whether it will light for 1000 hours, etc. In fact, I am giving one quotation by a Roman playwright Plautus, that is, everyone ought to keep a sharp eye on the main chance. So, there are several such statements that randomness is an indispensable ingredient of the human life. I will give some historical evidences. So, the theory of probability originated in the middle of 17th century. There are mainly studies by some mathematicians, namely Fermat, who was 1601 to 1665, Pascal between 1623 to 1662, Heinz 1629 to 1695, James Bernoulli between 1654 to 1705, etc. These are, you can say, some of the prominent mathematicians who started discussing among themselves various problems related to probability, and through their discussion and solving some of the problems, the subject probability started to grow. In fact, we can say that probably the physician and mathematician G. Cardano, whose time is from 1501 to 1575, probably he was the first to develop the systematic theory of probability. In fact, he was a gambler. That means he used to play gambling games of dice, coin, cards, and therefore, his interest in the probability was actually originated to find out the probabilities of various possibilities when he is playing a game of cards or when he is playing a game of dice. So, just to show you the photograph, he is actually Cardano. His work was published in 1663, much after his death, and it was a 15-page notebook consisting of 32 small chapters, the book on games of chance. And he solved a few problems which related to coin tossing, die throwing, etc. And you can say that he is the first one who systematically started to formulate the subject, you can say elementary concepts of probability. Thereafter, the subject was picked up by various other mathematicians, I named Fermat, Pascal, etc. And through their discussions, the subject started to crystallize. Now, what I will do? I will give you some elementary concepts of the probability, and through that I will give you some definitions of probability, through which the problems of probability can be solved. So, let us look at the terminology first. So, the first terminology is the term experiment. So, what is an experiment? In scientific terminology, an experiment is observing something happen or conducting something which results in an outcome. So, let us consider examples here. I gave you few examples in the beginning. Let me repeat some of those examples and say that how it is an experiment. So, I mentioned here whether tomorrow. So, here we are not conducting the experiment, rather we are observing, but the outcome will be observed. So, for example, whether it is cloudy tomorrow or whether it is very cold tomorrow or whether it is sunny day tomorrow, etc. So, we are observing. Similarly, I have given what is the height of a child. So, we are only observing, that means, we are not conducting the experiment, but something is happening and we look at the outcome. So, an experiment is observing something happen. Second is like conducting something which results in an outcome. So, this is like experiments which are done in the field of science. So, for example, you conduct experiments in physics, you conduct experiments in chemistry, you conduct experiments in biology, in genetics. There are large number of theoretical or practical experiments which are conducted in the laboratory conditions, where the outcome will be something. Now, there are two types of things. One is deterministic experiment. So, in the deterministic experiment, if after conducting the experiment we know the outcome of the experiment, we know the outcome of the experiment. So, for example, you know in your physics lab or chemistry lab etcetera, you conduct some experiments and many times you know already what will be the outcome. For example, a simple experiment is certain mixing of certain chemicals and then looking at the reaction. Since already this type of experiment is known, so you know what will be the outcome. The simplest thing is, for example, if you say two molecules of oxygen and a molecule of hydrogen, then you know that this is a formula for the water. Similarly, if I take a vessel and put water in that and we put it on a heater, we observe that the temperature raises to say 100 degree Celsius and the atmospheric pressure is say 760, then we know the outcome that the water will boil. So, these are some of the scientific experiments in which the outcome is known. These experiments are called deterministic experiments. In probability theory, we are not bothered about such experiments. We are bothered about experiments which are non-deterministic, which we also call random experiments. In non-deterministic or random experiments, we observe the experiment or we conduct the experiment, but the outcome cannot be predicted in advance. So, starting with the simplest one, like if we consider a coin and we toss it, then we do not know whether head will come up or tail will come up. If we toss a die, then we do not know whether you will get 1, 2, 3, 4, 5 or 6. If we consider a well shuffled deck of cards and we draw a card at random, then we do not know which of the 52 cards will come out. Now, these are some of the, you can say, textbook or classroom kind of experiments, but you generalize it to the experiments which I mentioned just now. So, for example, observation of the weather. So, no matter what scientific knowledge we have or how much scientific development we have, but to say exactly at what time, what temperature of the day will be there, with certainty we cannot say. So, therefore, there is uncertainty here, it is random experiment. Similarly, about the height of a child, the life of a person or life of an equipment. So, no matter how scientifically precise we produce a manufactured item, say for example, a light bulb, but can we say that what would be its actual life, whether it will be 5 hours, whether it will be 20 hours, whether it will be 1000 hours, we cannot say. Exact one cannot be, you may give a range, maybe you can say it will be between 5 hours to 50 hours or a statement like that. So, you can give an approximate statement, but you cannot give a fixed statement. Therefore, these are all examples of non-deterministic or random experiments. So, formally I can give a definition: when an experiment is conducted but the outcome cannot be predicted in advance, then it is called a random experiment. Now, one question arises: if an experiment is random, then what is the use of studying it? So, for example, I say that in a coin tossing experiment, the next toss will give me a head or tail that is not known to me, then why should I actually spend my time to develop a subject and study this thing? Now, the justification for this is that although in each trial I do not know whether a head will come or a tail will come, but in the long term, if I know or if we feel that the coin is unbiased or a fair coin, then maybe out of 1000 trials you will have a 500 heads and 500 tails, or approximately you may say 490 heads and 510 tails. If you conduct the experiment, suppose it is a biased, suppose you have a biased coin, then if you conduct it a long term number of times, then roughly the ratio of the heads to the tails will be actually the amount of bias that will be there. For example, if a head is say 3 times as likely to occur than a tail, that means it is heavily biased in favor of head. Then roughly if you conduct the experiment 1000 times, then maybe around 750 times you will have a head and 250 times you will get a tail. Now, this long term behavior is what encourages us to study the subject of probability theory. So, for example, if I talk about the weather, so every day there are weather predictions. So, the weather predictions are based on the long term behavior. So, like we say tomorrow it is likely to touch the temperature between 20 to 22 degree of Celsius in Delhi. Then it means that over the last 100 years or 150 years, that has been observed that this particular day of the year the temperature is between this. So, this long term behavior which is called statistical regularity. This is what encourages us to study the subject of probability theory, because although each experiment what will be the outcome at each trial we may not be able to say, but in the long term we know what is the proportion of the trials which will result in particular outcome. Now our concern is only to study the random experiments. So, when we are conducting a random experiments, we do not know what will be the actual outcome, but we know that the outcome can be something which I can enumerate. So, if we consider this enumeration, we make it as a set, then that set is called a sample space. So, we give a formal definition: the set of all possible outcomes of a random experiment is called the sample space. And we usually use the notation, set theoretic notation means some set. So, capital S, or sometimes we use the notation omega to denote So, let me give examples of some such things. So, suppose two coins are tossed. Now, when the coins are tossed, then what do we look at? We look at whether head has come or a tail has come. So, if two coins are there, then the possibilities can be both can be heads, both can be tails, one can be head and one can be tailed. Now, if two coins are there, then head and tail can interchange also, like first one is head, second one is tail, first one is tail, second one is head, etcetera. If we count like this, then the sample space can be written like this. So, please note my symbols here H H. So, this ordered pair denotes that on the first coin there is a head, on the second coin there is a head. Then you may have head on the first, you may have tail on the second, you may have tail on the first and you may have head on the second and you may have tails on both. So, this random experiment, that means, we have tossed two coins and we are looking at the outcomes. The possible outcomes are of 4 types. So, this sample space consists of 4 elements. Let me complicate it little bit. So, suppose we say, suppose a coin and a die is tossed together. Now, how to define the sample space now? So, we will have outcome for a coin and we will have outcome for the die. Outcome for the coin can be head or tail and outcome of the die can be 1, 2, 3, 4, 5 and 6. Now, since I am considering the experiment together, then I have to write the sample space also in the joint form. So, if I consider the similar set theoretic representation and an ordered pair will denote the first as an outcome for the coin and the second one as an outcome for a die, then I can write it like this. So, first one you can have coin occurrence as head and then you can have number 1 on the dice. You can have head on the coin, 2 on the die and so on, head and 6, then you can have tail 1 and so on, tail and 6. So, here you can see that there are 12 elements. There are 2 outcomes on coin and 6 possible outcomes on the die. So, 2 into 6 you have 12 possible outcomes in the sample space. Suppose I consider, say, what is the time of the day. Okay. So, for example, we are observing some event. Okay. So, at what time of the day that event occurred. So, now if you say time of the day, how are you going to observe it? That means, you look at the time in a clock. Now, the standard clocks, they will have 3 hands, one for the hour, one for the minute and one for the second. And when we observe them in the integer values. For example, hour will be 1, 2, 3 up to 12. Similarly, if you observe for the minute, then minute we will say 1 minute, 2 minute, 3 minute like that. So, starting from 0, because if it is at the full hour, then it is 0, then up to 59. Similarly, when you observe second, then second will be again 0, 1, 2 up to 59. Now, this is I am talking as an observer. See, if I say time of the day, then time can be from 12 midnight to next 12 midnight or 12 mid noon to another 12 mid noon. That means, you can have a 24-hour period and it is a continuous thing. But I am talking about when we observe and we report, then we report in terms of integer values for these hours of hand, minute and second. So, we may write the sample space like this. So, I am using the notation say S here. Now, it is a pair. So, I will say it is M N P. Okay. It is a ordered triplet M, N and P, where M can take values 1, 2 up to 12, N can take values 0, 1 to 59 and P can take values 0, 1 to 59. If we consider continuous time, then we may write the sample space as say 0 to 24. That means, any time between say 12 midnight to 12 midnight. So, if we are using the standard terminology, then 0 to 24, but here then I can take like even in the second I can split. So, depends upon the recording device that you are having, then we may write like this also. Now, one should not get confused between these two representations. When we actually solve a particular problem, then we have to fix our sample space. If we consider different sample spaces, then the different ways of attacking the problem will be there. I will give another example for this. Suppose I consider a 100-meter sprint race, say of Olympic standard. Okay. So, if we are considering Olympic standard, then there are 8 to 10 runners, let me call them P1, P2, P8. Suppose 8 runners are there. So, like how the experiment is conducted, that means all the players assemble at the starting point, and then there is a start, and the sprinters take their run and complete it in a certain specified time. Now, depending upon our interest, the sample space can be defined in different ways. So, for example, suppose I am interested in who is the winner. If we record the winner, then the sample space can be written as that means either of the 8 players can be the winner. So, it is P1, P2, P8. On the other hand, suppose we are interested in the winning time. If we are interested in then the sample space can be, let me write it as S2, since I said it is Olympic standard. So, interval can be say from 9.5 seconds to maybe 10 seconds. Here the recording is in seconds. Now, you can see that for the same problem I am having two descriptions of the sample space. Now, this is an important point. When we solve a problem of probability, then we should correctly specify the sample space. That means, your sample space is related to what type of thing you are interested in. If we are looking at a particular player being winner, and then we want to look at the probability of that, then we have to look at the possibilities of who can be the winner. So, this is the sample space. Whereas, if I am asking a question, what is the probability that the winning time will be a world record. So, for example, we know currently the world record is 9.58 seconds. That means, between 9.50 to 9.58, if the time is there, then it will become a world record. So, the time taken here, that will determine that the sample space has to be described in this particular fashion. Of course, there are different ways of answering these questions, but that we will come later when we discuss the various methods of finding out the probabilities. Let me take another example of the sample space. Suppose I am considering we record the number of accidents taking place in a city in a year. Okay. In 1 year, how many accidents have taken place? Now, how do you define the sample space here? So, maybe in the whole year there was no accident, 1 accident, 2 accidents and so on. Now, the thing is that what would be the upper limit? Here what happens that although theoretically we know that the number of accidents will be finite only. So, maybe there are suppose it is a small city. So, maybe there are 50 accidents in a year. Suppose it is a very large city like Delhi or Bombay, then the number of accidents may be running in thousands. So, maybe 10,000 accidents are there. Then how do you write? Like will you write 0, 1, 2 up to 1000? Actually, we do not need to put a upper limit here. We can write it as an infinite valued sample space here. What happens that when you allot a probability distribution based on certain methodology, then there will be higher probabilities allocated to the values which are in the beginning, and as the value increases the probability becomes very small. So, theoretically speaking we can put 0, 1, 2, 3 and so on ad infinitum, but practically most of the probability will be concentrated on a finite number of terms here. Similarly, if I am considering say life of an organism, okay. Again when we say life, then the life of most of the organisms will be finite. So, you can put an interval like 0 to say 100. Suppose I am recording in years, months, minutes, seconds, depending upon what kind of organism you are having. So, for example, if you are considering life of a human being, then you may consider say 0 to 150. So, if I say 0 to 150, this upper bound is actually only denoting that practically we do not observe a person living beyond 150 years, because normally we observe people living a life of 80 years, 85 years, 90 years, 95 years. There are people who are completing 100 years, but there will be normally very rare persons who are crossing say 110, because then their names will be coming in the Guinness Book of World Records, etc. And there will be hardly anybody who will be reaching the life of 150 years. So, it will be a practical way of putting the sample space. Otherwise, theoretically you may say okay, put 0 to infinity, okay. But in a practical sense we may limit our sample space as an interval 0 to 150 if we are recording in the years. Now, I will introduce other terminologies. So, first thing that we have seen in probability theory, we are concerned about experiments which are non-deterministic in nature. So, we call them random experiments. I have given several examples of that. Now, the set of all possible outcomes of a random experiment we call a sample space, and I have explained through some examples that how the various kind of sample spaces can be described. Now, the next thing is that what do we actually study in a probability theory. So, a question, a normal type of question I will say, what is the probability that the life of the bulb will be between 20 hours to 25 hours. So, when I say I am putting the life of a bulb say from 0 to 1000 hours, and I am asking a precise question 20 to 25 hours, then if I am considering the interval 0 to 1000 and out of that if I am taking 20 to 25, what it is? It is actually a subset. Similarly, if I say if a coin is tossed, I am getting a head or a tail. So, if I say what is the probability that there will be a head? So, what is head denoting? Head is one possible outcome out of the two possible outcomes here. So, this is a subset if I consider H of H and T. So, in general, when I am saying I want to find out probability of something, that something is called an event, and then event in mathematical terms is nothing but a subset of the sample space. So, let me then formally define. In probability theory, we are interested in finding the probabilities of certain possible outcomes. These collections, or you can say these collections of outcomes are called events. So, an event is a subset of the sample space. So, let us consider through various examples here. So, if I say tossing of 2 coins and I say event, I consider E as H t and T h. That means, this event is describing that one head and one tail is observed. Similarly, let us consider, say, I am considering the amount of rainfall during a monsoon season. So, amount of rainfall is recorded in millimeters, centimeters, etcetera. So, if I am considering for a full season, I may consider recording in centimeters. Okay. So, here the sample space can be say 0 to 200 centimeters. Okay. So, this is in centimeters. If I say I consider a subset say 50 to 75, then it means that the amount of rainfall is between 50 to 75 centimeter. So, here you can see this E is a subset of S. So, in general then what I am saying is that any subset of the sample space is an event. What you can observe here is that we are moving slowly towards mathematical representation of the probability. When I mentioned to you that in the 17th century or 16th century Europe, some of the mathematicians started discussing the problems of probability. So, they were talking like in tossing of a 3 dice, what is the probability that an 18 will be observed? In tossing of say 2 coins, what is the probability that one tail will be there, etcetera. This kind of problems they studied. Since they did not have the mathematical framework of set theory that time, so they were discussing it in a very verbose fashion by describing the event and then writing down lot of possibilities in essay type of language, and consequently they were trying to find out the solution. Sometimes they got it correctly and many times they got erroneous answers also. So, the reason was that they did not have the set theoretic framework at that particular time. The set theory, as you know, it developed only in the late 19th century by George Cantor. So, now when set theoretic notations are there, then you will see that the definitions and the consequently calculation of the probabilities becomes very simple. So, now the first thing I have mentioned, we have a sample space which is actually a set. the set of all possible outcomes. So, we have given a set theoretic notation. Now, the second definition I am talking about, that is of an event. So, event is nothing but a subset of the sample space. So, that means we are particularly trying to follow the notations of set theory here, and you will see that things become very nice, or you can say comfortable for actual definitions of the probability through this. Now, when I talk about the event, then we have several kind of events. So, as soon as we talk about an event, there can be some sort of vague statements that we use in day to day life. I am certain that it will rain in the evening, or you say, oh, it is not possible. So, that means we are giving some events, or you can say we are talking about something with certainty by saying that either it will actually happen or it will not happen. Now, these events are also considered in probability theory. So, we call them sure event. That means, the event that will certainly happen. So, for example, if we are considering tossing of a die, and if I say a number less than or equal to 7 occurs, then certainly it will happen. Of course, that means we are saying that the die will actually fall on a certain surface, and we observe the upper face of that. So, the number will be 1, 2, 3, 4, 5 or 6, because these are the 6 numbers which are there on the die. Of course, we are excluding the possibility that something supernatural may happen and the die may vanish, etcetera. But otherwise, we know that if we are specifying anything from the sample space itself, then it is a sure event. So, if I say in the monsoon season, the rainfall is less than 10,000 centimeter, then certainly it is sure event, because rainfall cannot be more than 10,000 centimeter during a monsoon season, because more than 10,000 centimeter means it will be flooding the whole of the country itself. So, that is not possible. So, if we want to use a set theoretic notation, then we can use S itself. To denote the sure event. That means, if all possibilities are counted, then it is a sure event, and the converse of it, or you can say complement of this, is nothing but the impossible event. Like if I say, if a die is thrown and we say that the number is greater than 10. So, in a die you are having numbers 1 to 6 and you say 10 will occur. So, it is impossible. So, this is denoting by null set or empty set, because that possibility is not there. We use the notation phi. Okay. Now, once we are describing the events by the sets, then naturally in mathematics you already have the notations of set theoretic operations. So, certainly if an event A is corresponding to set A, set B is corresponding to an event B. So, A and B are events and they are sets. Now, in the set theory we have union, intersection, difference, complement, etcetera. So, naturally that will lead to construction of new events. So, let me talk about that. So, union of two events. So, if I say A and B, okay. So, let A and B be two events, okay. Then A union B, in set theory it means that we are consisting of all the elements which are in A or B or both. So, here it will mean happening of either A or B or both. So, we can say like this: occurrence of either A or B or both. So, we can also say occurrence of at least one of A and B. Now, this representation is good because we can actually use it to write for more than 2 also. See, we can talk about union of 3 also, like A union B union C. Now, little bit let us take more mathematical notation. I will give some notation called union A I, that is I is equal to 1 to n. What is it means? I am considering A 1 union A 2 and so on union A n, that means union of n events. So, in mathematically you can find these sets, it means that elements are must be in A 1, elements must be in A 2, etcetera. That means, all the elements which are either in A 1 or A 2 or A 3 or in A n or in 2 of them or in 3 of them, etcetera, all of them will actually belong to union A I. So, this in probability terminology it will mean occurrence of at least one A I for I is equal to 1 to n. Let us extend it little bit more. We can consider union A I is equal to 1 to infinity. In place of a finite number of terms, I can consider even infinite number of possibilities. So, then this will mean occurrence of at least one A I, where I is equal to 1, 2 and so on. So, this union of two events I am able to describe in terms of events. That means, in event how it means? It means occurrence of at least one of them. Similarly, you have intersection of sets. So, that will lead to the interpretation for the intersection of events. So, for example, if I have A intersection B, in set theory it means that the elements which are common to A and B. So, in probability it will mean that simultaneous occurrence of both A and B. Now, likewise we can extend this concept to more than 2, that means A 1 intersection A 2 and so on intersection A n. So, it means simultaneous occurrence of A 1 A 2 A n, and we can further extend it A I is equal to 1 to infinity. So, this means simultaneous occurrence of A 1 A 2 and so on. That means, simultaneous occurrence of even all infinite number of these. Now, we have some further terminology. For example, you know the difference of sets A minus B. In set theory, what it means? The elements which are in A, but not in B. It has actually another representation also. We can also write it as A intersection B complement. Okay, complementation notation all of you know. If there is a universal set, then the elements which are not in B will be called to be in B complement. Okay. Now, in the context of probability theory, what is the universal set? So, here you can consider the sample space to be the universal set, because all the events are in the context of that only. So, here it will mean occurrence of A, but not of B. That means, A occurs, that is, but B does not occur. So, this is the interpretation for A minus B. Similarly, if I consider say event A, then what is the meaning of A complement? A complement will mean that not occurrence of A. Now, in set theory we have a concept of disjoint sets. So, if no elements are common, then the sets are said to be disjoint. So, if we say A intersection B is equal to phi, that means if A occurs, B will not occur, if B occurs, then A will not occur. So, we call them to be disjoint or mutually exclusive events. Now, if we further extend it, I can consider like A intersection B is equal to phi, B intersection C is equal to phi, A intersection C is equal to phi, etcetera. That means, several events are there, and in that each pair is disjoint. Then such events are called pairwise disjoint events. So, if I say A1, A2, An, suppose A1, A2, An are any events, okay, and we are having Ai intersection Aj is equal to phi for I not equal to j. Then A1, A2, etcetera, they are called pairwise disjoint events or pairwise mutually exclusive events. If I have a certain sample space and I am considering certain events out of that sample space in such a way that if I consider all of them together, then that gives me the full sample space, then they are called exhaustive events. So, if union of I is equal to 1 to n is equal to the sample space, then we say that events A1, A2, An are exhaustive. So, actually exhaustive meaning is that they exhaust all the possibilities of the sample space. So, that is why we call them to be exhaustive events. Let me just take one example here. Suppose I consider rolling of a die, then my sample space is 1, 2, 3, 4, 5, 6. Suppose I define event E as say 1, 3, 5 and F as the event 2, 4, 6. Then we observe two things about it. E and F are mutually exclusive. So, basically in terms of language, if I speak, then I will say E is the event that an odd number is observed, F is the event that an even number is observed. So, mutually exclusive means that because if an odd number is observed, an even number cannot be observed and vice versa. Secondly, if I consider all the possibilities, then they are either in E or F, because E union F is equal to S. So, E and F are exhaustive. This nomenclature of mutually exclusive and exhaustive will be the one which will be used for actually the first definition of probability. So, in the first lecture I have actually introduced little bit of historical context of the probability theory, where all it is useful, why we actually want to study this thing, and second is that some basic terminology has been given. In my next lecture, I will introduce the basic definitions of probability theory, how the probability is introduced, and then we will proceed to consider its advantages, disadvantages. We will look at some of the problems. So, in the next 4-5 lectures, I plan to give a basic understanding of probability theory, which is useful at class 11 and 12 level. Thank you.